Hello again. Let's get started. Today we're going to talk about the derivative in terms of increasing and decreasing. If a and b are real numbers such that a is less than b, and if f is a function from the open interval ab into r such that a less than x less than y less than b implies that f of x is less than or equal to f of y, then f is said to be increasing on the open interval AB. So as informally, as we're moving rightward from A toward B, f is moving upward in the y direction. F of x is moving upward. Our graph, we're moving up our graph as we're moving rightward from A to B. Of course, not including the endpoints A and B themselves. For all we know, at the endpoints themselves, we may not even be defined. We may not behave well even if we were defined. But in between, we at least behave well enough to be increasing. Okay, if we replace less than or equal to with less than in the definition here, if we put less than here, then this increasing becomes strictly increasing. So now, guys, because really we're inviting the possibility of equality here. There could be places where we're constant. What we're saying is as we go right from A to B, we'll never be going down. We'll either be flat or we'll be going up as we go rightward from A to B, but we'll never be going downward. We could be flat, though, because of this equal to piece here. However, if we do the strictly less than, if I was to put strictly less than here, there'd be no flatness. We'd strictly be going up and only up. We wouldn't even be so much as flat. That would be if we had the strictly less than here. Okay? And in a similar fashion, you can replace increase with decrease, and you'd have a greater than or equal to here. And you would be you would be on your way down. You would either be, as you go rightward from A to B, excluding A and B themselves again, not excluding, that is, with an EX, excluding A and B themselves, but for anybody on the interval from A to, on the open interval from A to B, as you go from A to B, F either falls or stays constant for this, because because you got this greater than or equal to here. If X is less than Y, and they're between A and B, then f of x is greater than or equal to f of y. In other words, f of y is less than or equal to f of x. So you're either staying flat or you're going down. Now, if you wanted to do purely decreasing, aka strictly decreasing, you could replace greater than or equal to with greater than. Okay. But anyway, I just did the analogous definition of decreasing and strictly decreasing that I did up here with increasing and strictly increasing. But anyway, there's that. Now, and again, with strictly, you would be strictly falling. You wouldn't be flat or constant at all with strictly. With decreasing, you possibly could be. There's that possibility. But anyway, let's move on. Let A be less than B, and let F be a function from the open interval AB into R, such that F is differentiable on the open interval AB. If F prime is greater than 0, then it can be shown that F is strictly increasing at that point X. We're not going to show that. I'm not going to prove it, but it can be shown. It can be proven. Now, on the other hand, if f prime is less than 0, it can be shown that f is strictly decreasing at x. And I do mean strictly. And if f prime of x equals 0, then we already know from previous videos that f is constant at the point x. Our tangent line would be flat there. If we were to break off and go off on our tangent line, it'd be flat there. F prime of x equals 0, we already know f is constant at x. So there's that. Now, example, let f be a function from the open interval 0 infinity into r such that f of x equals x squared. That's the classic parabola. Note that f prime of x equals 2x, which is greater than 0 if x is in the positives. Of course, 2x is positive if x is positive. Hence, f is strictly increasing for x, and I really should say for x in, that's better, for x in the positive numbers. That's the positives naturally being the open interval 0 to infinity. That's what we mean when we say the positives. Okay. Now, let f be the function from the negatives, that's this interval right here, into r, such that f of x equals x squared. Note that f prime equals 2x, but this time 2x is less than 0, which is aka negative, for all x in the negatives, because if x is negative, so is 2x right here. Hence, f is strictly decreasing on negative infinity to 0. And guys, you're out, well, Jason, how do you know that's true? I'm just parakeeting these rules up here. This is true because this right here is true. This right here, that is. This right here implies this right here. This whole example, this entire example. And this right here, on the other hand, implied from a minute ago this example right here. Okay. So, but anyway, there's that. And this right here is going to imply, well, this right here. Let f be a function from, guys, I was kind of silly here. The open interval neg infin to infin, that's just the reals itself. I could have just put r here. But this right here is going to imply this. The function from the reals to the reals, here's our old buddy, the parabola. And you know what? I kind of told you a bit of a lie a minute ago. This is actually this right here is the right half of the parabola. And this right here is the left half of the parabola. Oops, so I take it back. There's something, when I told you a minute ago that this is the classic parabola right here, it's not the classic parabola, it's the right half of the classic parabola. And this is the left half of the classic parabola. So sorry about that, guys. So this is the right half of the classic parabola. This is the left half of the classic parabola. And now this right here is the classic parabola. And for the entire classic parabola, f prime of 0 at the origin we're flat. F prime of 0 equals 0. We have a flat tangent line. And f is f is constant at the origin. We're neither increasing nor increasing at the origin. Okay. So there's that. And but anyway, so there's that. Now let's look at this example here. Now guys, notice that for increase and decreasing, if we go back to the definition, we only increase and decrease on open intervals. We don't like, notice that we even for increasing or strictly increasing, and likewise for decreasing or strictly decreasing, we don't like to do it on closed intervals. We do it on open intervals. It's kind of strange to do increasing and decreasing on endpoints. We don't like it, and we don't do it, okay? We just don't like it, okay? Let's not do it, okay? I don't think your professor would like it either, to be honest. So look, but consider the function from this closed interval, negative pi quarter to positive pi quarter into r, such that f of x equals the sine of x. Then f prime of x equals the cosine of x, which is greater than 0 for all x in the closed interval. So we're increasing on this corresponding open interval right here. Because remember, guys, I don't want to say that we're increasing on the entire closed interval because that's bad manners. It's just not a good thing to do. Just talk about increasing on an open interval, okay? If we wanted to push our luck and extend the domain of f, we could extend it to this entire open interval right here. But again, we couldn't really, can we say that we're increasing at these endpoints themselves? I would not do that if I were you. I'm not saying that that we're increasing at these endpoints. I'm just saying, you know what? are we increasing on this interval? I think it's safe to say that we're increasing on this interval. That should be fine. Yeah, that's fine. We are increasing on this interval. Yeah, that's fine, because after all, we're not including the endpoints themselves. But if you tried to extend this interval any further, even the smallest bit further, to the left this way, or to the right, to the left of negative pi halves, or to the right of positive pi halves, if you tried to go the smallest smidge further, you would mess things up. So don't do it. Okay. But anyway, this is as far as you can extend and still be okay. And at least as far as being increasing is concerned. Okay. But anyway, moving on. And if you ever say you're increasing on an interval, keep it open. Don't go closed. Okay. Don't put a bracket on any either the left or right side. Don't do it. Okay. But moving on down the highway. Let f be a function from the open intervals 0 to pi quarter into r, such that f of x equals the cosine of x. Then f prime of x equals negative 1 times the sine of x, or just neg sine of x, which is less than 0 for all x in this open interval. So we're decreasing on this open interval. And I need to put the result, don't I? Oops. Hence, we are decreasing, can't spell anymore, on this open interval. I can't even, sorry guys, I forgot to write the main result down, and I need to save this in the editing. I forgot to write the heart and soul result that we were looking for. So the whole point of this is we're decreasing on the open interval 0 to pi quarter. Now, if we wanted to push our luck as far as we could push it, we could extend the domain to 0 to pi. And we would be decreasing on that domain. Now, if you tried to go any further in either direction, you'd be out of luck and you'd mess things up. Okay? So absolutely no further, but you could go this far. But anyway. Let's move on. Let f be a function from the reals to the reals such that f of x equals the inverse tangent, or the arctan, that is. Then f prime of x is 1 over x squared plus 1, which is going to be greater than 0 by common sense, because x squared is a positive number, or 0 at least. It's not going to be negative. And then x squared plus 1 is not going to be any smaller than 1, and 1 over a positive is going to be positive. So the overall, so we have a positive over here, so that's naturally going to be greater than 0. So by common sense, this guy is greater than 0, so f prime, since it equals this guy, it's going to be greater than 0. So we have a positive f prime, but that's true, but x is arbitrary, so that's true for all x in the reals. Hence, we easily conclude, by since f prime is positive, since for arctan, f prime is positive for any real x, the arctangent is increasing on all reals. In other words, as we go from the left, guys, remember, for increasing, we always go from left to right. Back in algebra, when we talked about increasing, whether it's increase or decrease we're talking about, we go from the left to the right. If you rise as you go from the left to the right, you're increasing. If you fall as you go from the left to the right, you're decreasing. Okay? So if you rise as you go left to right, if you go up as you go from the left to the right, you're increasing. If you go down as you go from the left to the right, you're decreasing. So, but in this case, we're increasing because we rise. F prime is positive, so we're rising as we go. If you go left or right at all, anywhere, you're going to be going up. So we are increasing through all eternity. That's a really cool result to me. Oh well. So there's that. And let's see. Let f be a function from 0 from the positives. Let's move on. Let f be a function from the positives into the reals, such that f of x equals a square root of x. Then notice I left 0 out. I did that on purpose. Then f prime of x equals 1 over 2 radical x by previous videos. But that's always positive. Square root's always positive. But that's going to be always positive for all x in the positives. we have to, by the way, guys, x has to be positive for this right here to even be defined at all. Hence, f is increasing on the positives. So there's that. So that's a really cool result to me. So moving on. Well, my screen went crazy on me there. So let's move on down. Next, let a be less than b and let f be twice differentiable on ab. If f prime of x is greater than 0, aka positive, for all x in ab, then f lies above its tangent lines on ab, and we call it concave up by definition. The graph looks as though it's smiling upward. A prime example, think about y equals x squared, the classical parabola. Defined on all the reals. And in a similar fashion, again, let a be less than b and let f be twice differentiable on ab. Well, up here I said the classical parabola, it would be the classical parabola restricted to ab. So I guess I should be a little careful. It's the restriction of the classic parabola to the domain, the open interval domain ab. So I probably should be a little careful about that. But now, if we let's look at going back up here, consider the special case where a is negative infinity and b is positive infinity. And, well, if we allow a to be negative, let's just say that a is like a negative billion and b is a positive billion. And let's just say that f of x equals x squared. Then f double prime of x will be 2, which is, of course, greater than 0. For all x, for all x in negative billion to positive billion, truth be told, it'd be all x in the reals, but oh well. Then f lies above its tangent lines on this on that open interval, and we say it's concave up. So truth be told, you could actually go to negative infinity to positive infinity, but oh well. At least for the parabola y equals x squared anyway. There's other functions where that might not necessarily be true, or there might be other functions where that wouldn't necessarily be true, but I don't want to get neck deep into all that right now. But anyway, guys, remember y equals x squared, the graph look, and whether you want the domain to go from negative billion to positive billion or negative infinity to positive infinity, either way, the graph looks as though it is smiling upward. It has a smile to it. It's concave up. It lies above all its tangent lines. Y equals x squared is always smiling. Anywhere you go, whether it's to the left of the origin, to the right of the origin, it lies above its tangent lines. It's concave up. But anyway, and likewise, if you let a be less than b, and if you let f be twice differentiable, if we let f double prime be less than 0, then f lies below its tangent lines, and it's said to be concave down. The graph looks like it's frowning. Think about y equals negative x squared, the upside down classical parabola, and you can just let x go from negative infinity to infinity, or you could do an a-b interval where a is a negative billion and b is a positive billion. Guys, there's nothing sacred about a negative billion and a positive billion. I just picked something really negative big for a and positive big for b. You could let a be a negative trillion and b be a positive trillion for all I care. You could let a be negative 60 and b be positive 700 for all I care. Just pick something, okay? So, but anyway, coming down here, the upside down parabola looks like it's frowning. It lies, like if you drew any tangent, like if you picked a point and drew a tangent line for that point, it would actually lie below its tangent line. The graph would lie below the tangent line. It looks sad. The graph looks sad, whereas the classic parabola right here looks happy. But guys, I'll talk more about that in the next video. I'm running out of time. I'll see you on the next video. Bye-bye.